So Zeno's paradox is a problem that's not just of interest to mathematicians like myself, but it's also of interest to physicists and philosophers, and it has been for thousands of years. So Zeno was a Greek philosopher. He lived 2,500 years ago, and he came up with a list of paradoxes. There's about 9 of these paradoxes. The ones I want to talk about, though, are kind of similar. The first one, though, I love, because there's a nice little story with it. So the first one is called Achilles and the tortoise. You've got Achilles and the tortoise in a race. Now the tortoise is slower, of course, so he's given a head start. He's got a 100-metre head start, and then they start the race. Now Achilles sprints 100 metres and he catches up to where the tortoise was. But in that time, the tortoise has moved on. Right? He's moved on 10 metres. So Achilles now has to sprint to catch up with the tortoise again. So he sprints another 10 metres and he catches up to where the tortoise was. Now, since that time, the tortoise has moved on another metre. So Achilles has to sprint to catch up to where the tortoise was. And this keeps happening over and over again. So the paradox is, does Achilles ever catch up with the tortoise? And that's insane. And obviously he must do. We all live in the real world. He must catch up with the tortoise. Another of these paradoxes is basically the same, but it's a bit simpler. I'm holding my hands apart like that. Now I'm going to keep my left hand still. I'm going to move my right hand towards my left hand so that they clap. Now when I do that, you can think of it like I'm halving the distance, and then half the distance again, and then half the distance again, and again, and again, and again. And I half the distance an infinite number of times, infinitely many times. So does that mean that my hands never clap? Is there some sort of force field here stopping my hands meeting? Well, obviously they do. This is the paradox. So what's going on here? How can an infinite process end? What's going on? And this is part of Zeno's paradoxes. I want to give you the mathematician's point of view for this because, well, some say that the mathematicians have sorted this out. Let's say I start with my hands 2 metres apart and then I'm going to join them together. So they start 2 metres apart and then I halve the distance. So I've travelled 1 metre. And then half the distance again. So it now travels another half a metre. Then you do that again. You halve the distance again. So now your hands have travelled a quarter of a metre. And then it's an eighth, and a 16th, and 1/32. And then you keep doing this forever, halving the distance forever. Let's say this does have a value. Let's give it a value. Let's call it S. S for sum. Here's a trick that you can do. First of all, I'm going to multiply by a half. I'm going to multiply the whole thing by 1/2. So if I multiply the left-hand side by a half, you get half of S. On the right-hand side, I'm going to multiply term by term by a half. So 1 multiplied by a half is a half. Actually, I'm just going to write that there. I'm going to leave a little gap. Now I'm going to multiply the half by a half, which gives me a quarter. And I'm doing it term by term, so a quarter times a half is an eighth, and an eighth by a half is a 16th. Now I'm going to subtract those two things. If I subtract, on the left I get S minus a half S, which gives you a half S. On the right hand side, I'm going to subtract these two lines. So I've got 1, and I've got plus a half minus a half, plus a quarter minus a quarter, plus an eighth minus an eighth. And all the terms cancel out. So all you're left with is 1. Which means, if everything's cancelled out then, you can work out what S is. S is equal to 2. So this would be 2 metres. So your hands would travel 2 metres. Even though it's an infinite process, your hands do travel 2 metres. Now, time is important as well. If each step was taking a second, then that's an infinite number of seconds, or if it was longer than a second. So you would complete your 2 metres, but it kind of takes an infinite amount of time to complete your 2 meters. So time is important as well. So let's say, we'll do it a little bit faster than that. Let's say I move a meter per second. So I'm going to move a meter per second. It's the same working out. If I halve the distance, that would take me 1 second. And then I halve the distance again, would take me half a second, then a quarter of a second. So I could travel 2 meters in 2 seconds, and my hands would clap. So something like this, an infinite sum, behaves well when if you take the sum and then you keep adding one term at a time. So you've got lots of different sums getting closer and closer to your answer. Right? If that's the case, if your partial sums, that's what they're called, they're getting closer and closer to a value, then we say that's a well-behaved sum, and at infinity it is equal to it exactly. And it's not just getting closer and closer but not quite reaching. It is actually the whole thing properly. So it sounds like I'm saying that you can complete an infinite process. Now, an infinite process doesn't have a last step. So how can something without a last step be completed? And that's the paradox.
What is and is there a solution?
I have no easy answers for you here. This is a paradox that has baffled philosophers and mathematicians for 2,500 years. I wrestle with it as well. There are greater minds than you and I that have wrestled with this problem in the last 2,500 years. If this melts your brain, don't worry, you are in very good company.
Some of these numbers where the digits apparently go on forever, pi, square root of 2, how do they fit into all this?
Yeah, so if something goes on forever, it's almost like you're asking, like, can I even draw something that with these decimal representations that never finish? And it's the same sort of problem that we've got here. But again, even though that's an infinite process, it can be completed. And I know that's bizarre, but look, if I draw a triangle, okay, that has length 1, that has length 1, it's a right angle, and this has length the square root of 2. So, and there's no reason I can't do that, even though the square root of 2 is irrational, which means the decimals go on forever, even though it's like that, there's nothing stopping me from drawing it. In the same way, there's nothing stopping me from clapping my hands. You can think of this as an infinite process. I'm halving the distance an infinite number of times. But I can still clap my hands. So these 19th century mathematicians had to work out when these infinite sums behaved well and when they behaved badly. And so there's a lot of technical detail behind that. And it does turn out to be rigorous and consistent, which is very important. But some of the tests that you can use to prove that something is a well-behaved sum, well, they're quite easy. I'll show you one. What you can do is if you take one of these terms, I'm actually going to call it A. Like you take one of them, the nth term, an, you divide that by the one that came before it. And if it's negative, well, you'll make it positive then. If you take those numbers, if those numbers go towards a value, let's call it R, as these n's get bigger. Right, if these numbers tend towards a value, and if that number is less than 1, then it's well behaved. So this was well behaved. Why was this well behaved? Because if you take one of those terms and divide by the one that came before it, you always get a half. Look, a half divided by 1 is a half. A quarter divided by a half is also half. These are all halves, actually. You get a common factor of a half, a common ratio of a half for each one. That passes the test. And that's what this is a test. So it passes the test. This is well behaved. If this was bigger than 1, then it's not well behaved. And that could mean, well, it could mean it goes on to infinity. Or it could mean it's periodic or does something else weird. So it's not well behaved. And the other case is, if this number was equal to 1, we don't know. It could be anything. It could be either. It could be well behaved or not. It depends. So r equals to 1, we're not sure.
What's a series where r is like greater than 1? What can you show me? What's a badly behaved series?
So that if it was bigger than 1, then the terms would be getting bigger and bigger and bigger each time. Maybe not in a common ratio way, but well, we were talking about the Fibonacci sequence earlier. So if we had something like that, like 1 and 1 and 2 and 3, and if you divide those, they don't have a common ratio, but actually the ratio is tending to 1.618. The golden ratio. So 1.618 would be bigger than 1, and this would be badly behaved. If you added them together, you would get a number that was going off to infinity in that case, and that would be called divergent. This is well behaved, our example, and it's called convergent. My question to physicists is, if we were literal about this and considered the real world, so that we are actually dividing a distance repeatedly in half over and over again infinitely many times, or dividing the time it takes to complete each step infinitely many times, so it's getting quicker. Can you do that? Can you divide space and time infinitely many times? I don't know the answer to that, so I want a physicist to tell me.